Alright, so we're going to continue to look at our Maclaurin series expansion. Okay, so in the previous lesson we talked about how to, the steps, alright, step 1, 2 and 3 on how to use the formula that's given on my formula sheet. Okay, so this is the Maclaurin series expansion. Okay, so I've left it here for good reference. Now, in this lesson, let's take a look at an example. I guess it's best learned through examples. Okay, so I'll show you the steps and I'll also share with you some tips and tricks to make solving this kind of question a lot easier. Okay, so the question goes, expand y equals to ln ex plus 1 up to the first four up to and including the first four non-zero terms. Okay, and what I didn't write over here is that usually in your exam questions they would say using the Maclaurin series expansion. Okay, so we know that in this case we are not using the standard series formulas in this case. Okay, yes, you can see this one is just simply going to be ln bracket 1 plus ex, right? And this one could be expanded using the standard series formulas. Okay, it's the kind of question where you have a series within a series. But in this case, we are not looking at those. Okay, so let's not be confused about that. And usually in your exam questions, the paper will tell you upfront. Okay, so using the Maclaurin series expansion formula, something to that note. Okay, you know that. Okay, in that case, you're going to use this guy over here. All right. Okay. Now, so for the purpose of demonstration, obviously for this question, we're going to use the Maclaurin series expansion instead of using the standard series. And step number 1, if you recall, we talked about actually going to figure out what is our f prime x, f double prime x, so on and so forth, right? Now, for the first four non-zero terms, usually it would mean this guy, 1, 2, 3, 4, okay? But usually there is a twist with this kind of question, okay? So tip and trick over here for you. When you see that it's a non-zero term, just have kind of like a be careful over here, because what happens is that if they knew that the first four terms, okay, all right, the coefficient, the constant and the coefficient of the x squared and x cubed, if they knew that you know, it's not going to be 0, then in those cases they would just simply ask you to, you know, do it up to the term including x cubed. All right, but this one is very peculiar here. When they say non-zero, be careful. All right, usually there is something hidden here. Okay, so this is a tip for your exam. When it says non-zero, it means that either somewhere along this expansion in ascending order, some of the terms, okay, has coefficient 0, and as a result, for example, let's say this one turns out to be 0, f double prime 0 is actually 0, so this term is gone. And if you were to just give the first two terms and this guy, okay, at the back, there's only 3 terms. You will not get your full marks, okay, because they ask for 4 non-zero terms. So as a result, you would have to move forward and give them the next one, which will be up to x to the power of 4. All right, that will make it 1, 2. This is 0, right? And then 3, 4. Okay, for example. So be careful here. My point is, when you see non-zero, it's not always just going to be 4 terms, and therefore all you need to do is just get the expression up to d3y dx cubed. Okay, in this case, you can expect more. All right, just be careful there. Okay, so I purposely choose this question because this is something important here. Now, over here, we're going to do step 1. So step 1, we are going to figure out what is all this. So in this case, as we know that we could just write dy dx because this is defined as y, which is your fx, right? So we could use the expression dy dx to mean f prime x, okay? So we could differentiate this, all right? And then we have 1 over ex plus 1, okay? I assume that you know how to do a differentiation, yeah? So this goes down, and then we're going to do the chain. So we're going to differentiate this guy, which actually is going to give us this, okay? Now, you could continue and figure out what is d2y dx squared. You could continue from here, and then from here on, what you need to do is to use quotient rule, right? Because this is a function in x in the numerator, this is a function in x in the denominator, so you have two different functions. You got to use the quotient rule for differentiation, and that will give you ex plus 1 holding square, okay? And then you have to keep this guy ex plus 1, and then you differentiate this guy and then you got a minus, so on and so forth. Now, I don't want to continue this. This can be tedious, okay? If you want to head down this direction, it's not wrong, it's just tedious, okay? At the start of the lesson, remember, I promised you that I'm going to share with you some tips and tricks to make solving these kind of questions easier, right? So we're going to take a look at an alternative method, which is not so tedious, all right? Okay, now, let's get back here. What we'll do is this, okay? I want you to, there's no hard and fast rule to do this. So what you need to do is really to put your thinking caps on and observe the pattern, okay? What you can see is that I have an EX plus 1 over here, right? And there's an EX plus 1 over here. So the whole idea is now about looking at the expression that we have and trying to simplify by substituting values from the previous expressions that we have. So for the dy dx, the previous expression that we have is only the y equals to ln ex plus 1, okay? So in that case, I'm going to substitute out so that some of these terms will be in terms of y, all right? Now, take a look at this guy. We have the ex plus 1 over here, we have the ex plus 1 over here. So what I can do is this. I could change this expression, right? So let's just write it over here for reference. We have ln ex plus 1. And then when I were to take the power e on both sides, I have ey is equals to ex plus 1. Okay? Alright? So if you need the intermediate steps, this is how I get it. Okay, so we got e to the power y is equals to e to the power ln ex plus 1. Okay? And e to the power ln is actually, it cancels out and it gives you ex plus 1. Okay, I often have students that will ask me how I get from here to here. Usually I'll prove it to them in class, but this is not the purpose of our lesson over here, so I'm gonna skip that part and just move forward. But I will tell you that in order to just convince yourself quickly, and it's not no matter what, it's not a proof, but you can go ahead and type e ln 5 and you realize that you actually get 5. You go and type in e ln 10, you actually get 10, okay? So just to tell you, just to give you a feeling that it works, but there is actually a proper proof for this, okay? But we can talk about it in some other time. Now, as a result of this, okay, you realize that we have the ex plus 1, okay, which is actually equal to ey. So that means I could simplify my values a little bit, okay? So this would mean that I have over y, okay, right? Look, oh, sorry, e to the power y, okay? All right, that's over here. And then there's the ex here. Now we got an ex here. I can make ex a subject formula by moving the 1 over to the other side. So this is actually e to the power y minus 1. Now, we can simplify this even further because we can split this fraction into 2. So we got ey over ey, that gives me 1. And then on this end is minus 1 over ey, right? Can see? Okay, here, cancels out, gives me 1, then minus 1 over this. Now, the next thing is this. I could also make it look like this. Okay, we just apply the indices, right? Laws of indices, so we get this. Now, compared to this guy, which one would be more easy, or rather easier to differentiate? Okay, this one or this one when you try to get d2y dx squared. So, in my opinion, it would be this guy, all right? And I hope that you agree with me. Okay, so that is the whole idea over here, right? We will. Okay, we're still in step 1. So we will try to simplify the expressions so that it makes our job easier as we approach the higher derivatives. Okay, this is much easier to differentiate. So if I were to differentiate this, okay, I'm going to get e minus y dy dx. Okay, this is when we are differentiating with respect to x. Okay, so you must learn implicit differentiation in order to understand this. Okay, we're going to differentiate this guy. So 1 is gone, then the minus. Okay, we keep it. We keep the minus actually. Okay, and then after that, you differentiate the e minus y, which will give you minus e minus y. All right. So as a result, the negative cancels out each other. That's why I'm not writing anything here. Okay. So that leaves me with the e minus y. But with the implicit differentiation, since we are differentiating with respect to x, you need to multiply it with dy dx. Okay. That is just a very quick explanation on implicit differentiation. Now I'm going to save some space, so I want to use the space over here. We're going to do d3y dx cubed over here. Alright, so what do we have? Now, it's a function multiplied by another function. Alright, so in that case, what happens is that we got to use product rule. Okay, so we're going to keep this guy first, e minus y, and then we'll differentiate this guy, right? So when we differentiate this guy, it's going to give you d2y dx squared. Okay, you differentiate dy dx, it's just simply d2y dx squared. And since it's product rule, we're going to do the reverse. So we're going to keep the dy dx this time, and then we're going to differentiate this guy. Now, when we differentiate this guy, it's going to give us e minus 1, and then we chain it. Oh, sorry, e minus y, and then we chain it, it's going to give us a negative, isn't it? So that changes the sign to minus. Okay, again, we're going to keep the dy dx, differentiate e minus y. Okay, we're going to differentiate e minus y. So we're going to write here for illustration. So we will have e minus y. We chain this, it's going to give us minus e minus y, right? Because minus y, when you differentiate, it gives you minus 1. But because we're differentiating with respect to x, then we will have to multiply it by a dy dx. So as a result of this, excuse me, we have an extra dy dx over here. Okay, so this is it, right? But notice that this is 2 dy dx, so we can actually combine this together. So I'm going to erase this, just remember that. Okay, so we have e minus y, and then we have the dy dx. We can combine it together and give us dy dx whole thing squared. Okay, so this is it. That is how we get a d3y dx cubed. Now, I know we talked about the first 4 non-zero terms, and I am expecting that, I don't know, maybe 1, maybe 2 of these are going to turn out to be 0 terms, okay? Nonetheless, what happens is that you could go ahead and do a d4y dx4, but we're just going to leave some space for that later on, okay? So I know that most likely I need to do one more, okay? But we're going to just leave it at that first, and then we move on.